Hi everyone, I hope I am audible. Can you please confirm if my voice is fine or there is some issue in my voice? Okay, I hope I am audible, right? So today we are going to discuss few more questions of memory management. And in the last session we have discussed few questions, but in today's session we will just discuss few more questions. Okay. So can you please confirm if my audio and video everything is fine? Hi Harish. Hi Shumant. Okay. So let's just get started, right? So let me directly pose the problem, what we are going to solve. I mean, the first problem that we are going to solve today. And those students who are just watching me first time, let me just quickly introduce myself. I'm Sachin. I'm currently co-founder and instructor at GoClasses. I have done my master's from Indian Institute of Science, Bangalore, which is ISC Bangalore. And after that, I have worked at Amazon as an applied scientist. And I have also achieved GATE All India Rank 33. Okay. Yeah, this is my brief introduction. So let me just start with the problem that I want to solve today. So basically, now we are going to solve two very important question or very nice question you can say. One was asking GATE 2003 and another was asking GATE 2021. So these two questions are almost similar to each other that we are going to solve. Okay. And these two questions are basically taken from, the idea is taken from one of the question that is available at this university. So what we are going to do, we are going to first solve this question, and this question itself has two parts, three parts, but these two parts are big. So these two parts, this part has been asked in GATE 2021, this part has been asked in GATE 2003. So we are going to solve these two parts first, and that will give you the idea of the problem, type of problem that we are going to solve, and then we will be solving GATE 2003 and GATE 2021 question, right? So let me just start with this question. I hope that is fine to everyone, right? Okay. So let's just get started. Now what they are saying, in a 32-bit machine, we subdivided the virtual address into four segments like this. So the address split is given, which is the virtual address split that is given like this. So maybe I can copy this to the next page. Okay. So they are saying that this is the address split that is given to us. And then what they are asking is that they are saying that this is 3-level page table, such that the 10-bit are for the first level and so on, which means this is the first level they are saying, right? And this is for the second level, this is the third level. That's what they are saying. Now what they are asking is that what is the page size in such a system? Okay, so the first question is that what is the page size? Can you tell me the page size? I think this is the easiest question. How to get this page size? It is very easy. How? You will say that okay, page offset is 8 bits, so that's why page size is 2 power 8 bytes, right? Which is I think this is 256 bytes, right? Let me know if that is fine to everyone. So this is how very easily you can find out the page size. Now they are asking a few more important questions, right? Not just this page size. So let's just let's just look at those important questions. What is the first question they are saying? Now they are saying, okay. So the second question they are saying is that what is the size of page table for the process that has 256 kilobytes of memory starting from the address 0? So let me first explain that what does this question mean, and then we will solve this question. So what this question is saying that what is the size of page table? Okay. So what does it mean? Let me just tell you. So see, like the total virtual address space is given to us, which is basically 32 bits, right? Which is like this. So the total virtual address space is this. Now, a process may not be using the total virtual address space. What do I mean by that? See, this will actually clear up your one very important doubt or very important concept, which is that how multi-level paging is reducing the size of page table. Okay. So let me first explain this, and then this will clarify very important thing in the multi-level page table. So see, suppose that this is your virtual address space, right? This is your virtual address space. Now this is having different areas, which is stack, this is heap or something like this, right? Maybe this is code, this is data, this is heap, something like this. Now, suppose I write, this is your virtual address space. Suppose I write a simple program, which is something like this. Maybe if I write a simple program, main, okay, int a equal to 4, maybe, and then if I write int b equal to, let's suppose malloc, okay, int star b equal to malloc or something like this, right? Suppose I write this small program. What do you think? How much it is going to take? Maybe for A it will take 4 bytes. That might be in the stack, right? Maybe for B it might take some bytes, right? And in the heap, like this B will be also in the stack, and the heap will be having the 4 bytes. This malloc will be giving the 4 bytes from the heap. So if I draw the layout for this, then you will say the stack will be, in the stack you will be having some A, and the B variable is in the stack only. These are in the stack only, which is the main stack. Stack of main.c, and then main function. And if there is some other function, then there will be another stack on top of this stack. But currently, let's suppose this is the only function. Then maybe from the heap you are allocating the 4 bytes. So this is a heap, and B is pointing to those 4 bytes. Suppose those 4 bytes are somewhere here that you have allocated from heap, and then there will be a data section. I don't think the data will be having any significant bytes here. Similarly, the code will also be very small. So what do you think the total number of bytes it's going to take? Total number of total size this process is going to take. This process is going to take probably maybe let me say the 4 bytes here, right? If the integer is of 4 bytes, let's suppose the pointer is of 8 bytes, then 8 bytes here, probably 4 bytes here, something like this. Total it might take, let's suppose the 20 bytes or 20 bytes, 30 bytes, something like this, right? So it might take just a small number of bytes. Maybe let's suppose 20 bytes is taking the total. Right? This program is going to take just 20 bytes. Is this okay to everyone? I'm just assuming that it is going to take some small number of bytes. So let's just keep it 20. Now, let's suppose your virtual address space is huge, which means let's suppose it is 2 power 32 bytes, which is I think 2 power 20 is MB, 2 power 30 is GB. So which is I think 4 GB, somewhere around 4 GB, right? This is, let's suppose your virtual address space is 4 GB. It is just taking 20 bytes, which is negligible. So your process is basically going to take just 20 bytes. Still your virtual address space is 4 GB, right? So where do you think the gap is? Gap means the where is the most unallocated area in this virtual address space? Because the stack and heap are not growing much. So I think the most of the area here is empty, right? Most of the area is empty. I hope you understood my point. So basically what I mean to say is that there are two things that I want to introduce. One is that virtual address space size could be anything, which is in this case 2 power 32 bytes, which is same as saying 4 GB. And your process size, right? Process size, in fact, maximum it could go to 4 GB, because that's what we are saying to the process. But in reality, right? In reality, the process could be just 20 bytes, right? Many such processes can be there in reality, right? So is this okay to everyone? That what do I mean by saying what is the virtual address space, and what do I mean by saying that what is your process size? Your process size could be basically very small, right, compared to the virtual address space. Now what we want to check, that if I want to use multi-level paging for this process, then how it is going to help us. Okay, so what do I mean by that? See, this is your virtual address space. Currently this is your virtual address space. Here this is your stack, and this is your code. Let's suppose this is data, this is, let's suppose, heap. Okay, and what I'm saying, since it is taking very pages, maybe this pages, something like this, and then we will say that I will store the first page into some frame, I will store the second page into some frame, and for that I will be having a page table, right? So this is called a flat level page table. So let's suppose there are, let's suppose these, right? This page is getting allocated to which frame? So inside I have the frame number, and that's what we call page table. I hope everyone agree with me. This is called page table. Now interestingly, one thing is to be very noted here is that most of these pages, most of these entries are invalid, because you are going to allocate this page, you are going to allocate maybe this page, this page, this page, maybe 3-4 entries are valid. Otherwise these pages are not having any valid data, so you will say that maybe this page, this is valid entry, maybe these two are valid entry, apart from them all of them are invalid entry, right? Invalid entry. So that's the problem with the flat level page table. Even though these are the invalid entry, you have to keep them, right? So this is the problem with the flat level page table, and multi-level page table actually, multi-level paging actually overcome this idea. And that's the very interesting and very nice, very important motivation of the multi-level page table. Like why we do multi-level paging? Because in flat level paging, right? In flat level paging, in flat page table, we keep all entries even though most of them are right. We have to keep it, there is no other way. So how multi-level paging is solving this idea? Okay, so let's just see with this example, and then you will get to understand that how multi-level paging is solving this idea. Have you understood the problem behind the flat level page table? Let me know. Now we will see that how multi-level paging is actually overcoming this idea. First, let me know if you are able to understand the problem behind the flat level page table. Okay, and then once you confirm me, then we will move to the multi-level page table. So let's just see that how multi-level page table can overcome this idea, right? Okay. So let me go to the next page and let me just show you that how multi-level page table is actually helpful here. So now what they are saying is that there is a process or there is a program that is having a size of just 256 kilobytes, right? So they are saying that okay, in general your program uses discrete or may not be continuous set of pages, which means it is using this page, this page, this page, something like this, right? 3-4 pages it is using out of the 1000 pages that we talked about, but these 3-4 pages could be the scattered around, which means 3 pages may be here, 1 page is here, something like this. But what they are saying, I mean, just for the sake of simplicity, they are saying that in your virtual address space, your program or your process is just using 256 kilobyte, that is starting from 0 to 256 kilobyte. Okay, 256 kilobytes, this space you are using of your total virtual address space, right? Which means your stack heap everything is here, right? I mean, just hypothetically they are saying it. Now what they are saying that what is the size of page table that we require if we do the multi-level paging, which is the 3-level paging here that we are doing, right? So 256 kilobytes means what? This is the process size, which is 256 kilobytes, which is actually same as 2 power 8 into 2 power 10 bytes, which is actually same as if one page is of 2 power 8 bytes, then it is 2 power 10 pages, right? Which means your process is actually using just 2 power 10 pages, so which is same as 2 power 10 pages, right? Okay, that's great. So I hope you understand that my process is just using this many bytes, that it means that we are just using 2 power 10 pages. Now let me just see that what going to happen in the paging. So see, this is your process, right? I mean, this is your virtual address space. You will divide this virtual address space into pages, and from 0 to from this 0 to some address, and the total 2 power 10 pages, 2 power 10 pages is actually being used. And total pages could be many, right? Total maybe 10 plus 8 18 plus 6, 18 plus 6 is 24. Maybe it is total 2 power 24 pages, right? Maybe total 2 power 24 pages are there, and out of them only 2 power 10 pages are using. So virtual address space is 2 power 24 pages, but my process size, right, my process is very small. Process is just using 2 power 10 pages. I hope this is clear to everyone. Now I want to just clarify one very important, very nice motivation, very important thing about the multi-level paging is that how multi-level paging is actually helping me here. If my process size is smaller, then how multi-level paging is actually saving the page table size. Okay, so that's why that's what we are interested in to know. Okay, so I hope that is understood. Now let's just move further. Now let's just talk about the flat level page table. Okay, so if it is flat level page table, let me just write, if it is flat page table, then what you will do, you will have a page table. Can you tell me how many entries will be there in the page table? Number of entries is equal to number of pages, which is 2 power 24 pages you have. Out of them, how many valid entries? Okay, number of valid entries not have more than 2 power 10. Is this good enough to everyone? Right? So uh, total there are 2 power 24 entries. That's what the flat level page table has, right? Total 2 power 24 entries. So here, out of them, only 2 power 10 are useful. Anyway, let's suppose these are 2 power 10 entries, which are, I'm saying, valid entries at any moment, and out of all other entries are actually wasteful. But anyway, let's not worry about it. But you have to maintain this page table, right? This is a flat level page table. There is no idea, I mean, no other way. You have to maintain this flat level page table. Since the like pages may grow dynamically, which means that you do not know that you only need 2 power 10, right? You never know you only need 2 power 10. You maybe see, this is just a future I'm telling you. I mean, I know that I have written the program, right? I know that, see, this program was written by me, so I know it is just going to take 20 bytes, which is just one page, right? Just maybe even lesser than one page, so I know it. So let's suppose that somehow I know that my program is never going to take more than 2 power 10, but OS doesn't know, right? So OS will allocate a page table which is capable of holding 2 power 24 pages total. But anyway, you are never going to use those 2 power 24 pages, so you are just going to use 2 power 10 pages. So actually these are invalid entries, but still we have to keep them. That's the problem with flat level page. Flat level is equal to 2 power 24, because these are the number of entries. Let's suppose page table entry size is 2 bytes, right? So it will be 2 power 24. These are the number of entry into 2 bytes, which is 2 power 25 bytes, which is same as 32 megabytes. Sorry, yeah, I think that is right. 32 MB, right? So if you go for the flat level page table, it is 32 MB. Is this fine to everyone? Okay. So now let's just see, if we go for the multi-level paging, then how it is helpful, right? Now let's just see, if we go for the multi-level paging. Okay, is my internet dropping in between? Okay, just a second. Thirty-two MB. Now we want to see if we can improve using the multi-level page table. Let me know if this calculation is fine to everyone. Okay. So what they're saying that we are using 3 level of page table, and now tell me if you can improve from this 32 MB. And this has been asked many times in gate. Okay, that, I mean, there are many true false statement that says, okay, I mean, there will be true false statement that will say that multi-level paging, okay, multi-level paging reduces the page table size. Is this true? So answer is true, and we will see that how it is true today. Okay, we will see it. Now let me directly go to this thing, which means that we are using the 3 level of paging, right? So there are total 2 power 24 pages, but we are just using 2 power 10 pages, and how this 3 level of paging is helping us to save the page table size. Hello. Okay. I hope that is now better, right? Okay. So can we start? Cool. Okay. So let me just start. What I was saying that let's just check how the multi-level paging can help us here. Let me just copy it. So here what we are saying is that we are using the multi-level paging, and this is the current virtual address space split, right? Now tell me, what will the first level page table or the third level page table, how many entries it will be having? It will be having 2 power 24 entries, right? It will be having 2 power 24 entries, because these are the 2 power 24 pages we have, because we have 2 power 24 pages. So that's why we will be having 2 power 24 entries here. Now in each chunk, how many entries I will be having in each chunk? Okay, so total 2 power 24 entries, that I completely agree. But in each chunk, so I will be dividing that into chunks also, right? Can anyone tell me in each chunk how many entries I will be having? 2 power 6 entries, right? So in each chunk I will be having 2 power 6 entries. Now since I need only 2 power 10 entries, so 2 power 6 entries I will be having in each chunk. Now since I only need 2 power 10 entries, can anyone tell me that how many chunks I will be needing? See, 2 power 10 entries are the valid entries that I have, and 2 power 6 entries each chunk is having. So basically 2 power 6, which means 2 power 4, 2 power 4 chunks will be having the valid entries, right? These chunks will be the valid chunks, otherwise all of the chunks will be the invalid chunks. Is this okay to everyone? So 2 power 10 upon 2 power 6, which is 2 power 4. So I will say 2 power 4. 2 power 4 chunks will be having some valid entries. So these are the chunks having valid entries, isn't it? Let me know if that is fine to everyone. So see, there are how many chunks or something like that? Like, I mean, you can definitely calculate that there are 2 power 18 chunks, and out of those 2 power 18 chunks, only 2 power 4 chunks are having some valid entries. Or maybe you can say that okay, each chunk is having 2 power 6 2 power 6 entries, and since I just need 2 power 10 entries, so that's why only 2 power 4 chunks are useful to me. I mean, there are many chunks. How many total chunks are there? 2 power 18 chunks are there, right? Since there are total 2 power 18 chunks, but out of those only 2 power 4 chunks are useful. See, if you're not getting this, like how I'm calculating the chunks and all, please watch the previous session. Okay, in the same playlist you can watch the previous session. There I have explained it very clearly, right? So yeah, so now I hope you understood that out of all the chunks, only 2 power 4 chunks are good to me. So let me write it. See here, only 2 power 4 chunks are good, which means you can immediately say that, see, here I need only 2 power 4 chunks are good to me. Remaining chunks, that whatever chunks you are having many chunks here, which is 2 power 18 chunks, I think, right? So remaining chunks we do not need to have. What do I mean by that? I will just clarify in just a minute. So here, let's suppose there are many chunks, and out of those chunks, let's suppose these are 2 power 4 chunks. Let's suppose only these chunks are helpful, and apart from those 2 power 4 chunks, every other chunks I don't need. I actually don't need these chunks. Okay, I hope that is, at least that is clear to everyone. Now tell me, in the next level, okay, this is the third level, in the next level how many entries are useful? See here, 2 power 10 pages were useful, that means 2 power 10 entries were useful, that I translated to chunks. Now here tell me how many entries are useful? Here 2 power 4 entries, because each chunk is just one entry, right? Each chunk will be just one entry here. Each entry will be pointing to one chunk. Each entry will be pointing to one chunk. So basically here 2 power 4 entries are useful, which means what? How many chunks can you convert that to chunks? Each chunk size is 2 power 8 entries. So that's why you can say that only one chunk is required, because one chunk is capable of holding 2 power 8 entries, and you just need 2 power 4 entries. So one chunk only, right? So which means only one chunk is needed here. right? Similarly, you can say here I needed 2 power 10 entries, and I translated the 2 power 10 entries to chunks, that is coming out to be 2 power 4 chunks. So 2 power 10 entries were needing here, that is coming out to be 2 power 4 chunks. Similarly, at the last level, since only one chunk is helpful, I mean one chunk is helpful here. So how many entries are needed here? Only one entry, right? Only one entry I need, which means, I mean, each chunk is having 2 power 10 entries, but that's okay. I need at least one chunk here, right? So I will be needing one chunk here. So I need one chunk here. I need one chunk here. I need 2 power 4 chunks here, which means to translate at any moment of time, I need just one page here, one chunk or one page here, and 2 power 4 chunks here, and I can translate any virtual address to the physical address, isn't it? Because I never have to refer. See, this is one. There are 2 power 10 chunks, right? Sorry, there is just one chunk which is having 2 power 10 entries, and only one of the entry will point to something valid. All the remaining entries are, I never need to use all those remaining entries, right? So I will point here, and from here there are 2 power 8 entries, but only 2 power 4 entries are useful to me. Let's suppose these are only 2 power 4 entries are useful to me. So this is pointing here, this is pointing here, something like that, right? And based on that, I will be going here, and I will never need to point to these things. I never need to point to these things, right? I hope that is fine here. So how many page, how much space I need? I need one chunk here, which is basically, let me just write in terms of entries. So I need one chunk which is actually 2 power 10 entries I need, right? So basically, let me write it. I need okay, let me write it in this way. I need one chunk here. See, I need one chunk at this level. One chunk definitely I need at this level. One chunk I need at this level, and I need 2 power 4 chunks at this level. So if these chunks are available to me, then I can translate any virtual address to the physical address. That's the deal, right? Okay. Now this one chunk means, this one chunk means 2 power 10 entries. 10 entries. This one chunk means 2 power 8 entries. This 2 power 4 chunks means 16. Each chunk means 2 power 6 entries. So that's why these many entries, right? So in terms of entries, I need 2 power 10 plus 2 power 8 plus 2 power 10, right? These many entries I need. And let's suppose each page table entry size is, let's suppose, 2 bytes. So how many bytes I need here now? 2 power 10 plus 2 power 8 plus 2 power 10 into 2 bytes, which is basically 2 power 10 plus 2 power 10 is 2 power 11. So it is 2 power 11 plus 2 power 8 into 2, which is you can say 2 power 12 plus 2 power 9 bytes. Okay, and I don't know, you can take 2 power 9 plus 2 power 11 bytes. You can take 2 power 9 common. It is 1 plus, I think, 2 power 2 bytes, which is 5 bytes. So basically you can say this is 512 into 5 bytes, right? So these many bytes only, which is actually, maybe, I don't know. So yeah, if I just ignore, maybe, okay, you can just multiply it. So it's just in just bytes, right? So maybe if I just write it over approximation, instead of 5, let me just write it 8. Okay, just for the over approximations. Okay, so basically it is 2 power 9 into 2 power 3, which is 2 power 11 bytes, which is 2 into 2 power 10, which is 2 kilobytes, right? 2 kilobytes. So it is just 2 kilobytes, which means if you are using multi-level paging, then you just need 2 kilobytes of the page tables. But earlier, do you remember how much you were needing? Earlier, anyone remember? Instead of 2 kilobytes, I think it was in megabytes, right? So it is 32 MB. So now you just compare that like if you're using the multi-level paging, then it is just 2 kilobytes, and if you're using the flat level page table, then it is actually not taking care of that. Okay, I need these many entries only. You have to maintain all the entries if you're just maintaining one chunk. One page table, right? Then you have to maintain all the entries. You have to take all the entries. because this is the outermost page table. In the outermost, you have to take all the entries. So similarly, I'm doing here the same thing. In the outermost, I need the complete chunk. Here only if one entry is useful, that is okay. I cannot just keep the one entry here. I need the one chunk here, right? So that is how multi-level paging is saving our space. I hope that is understood to everyone. Let me know if there is any doubt. Now let's just do one thing. Let me just try to solve this question. Okay. Yeah, this question which has been asking GATE 2021. So this question has been asking GATE 2021, and let's now try to solve this question, that what they are saying. So they are saying that consider a 3-level page table with this translation, which is having 39-bit virtual address, right? Okay. So now what they are saying is that the page size is 4 KB, which is 2 power 10, and 2 power, okay, 1 KB is 2 power 10, and that's why it is 12 bytes, 12 bits. So that's cool. Now they are saying the page table entry is given to be 8 bytes. A process P is running, and that is just using 2 GB. Okay, so see what they are saying, that even though your virtual address space is 2 power 39 bytes, which is actually, I think 2 power 30 is 1 GB, which is 2 power 9 GB, right? Which is a huge space. You have your virtual address space is huge, which is 2 power 9 GB. But they are saying that my process is small, that is just using 2 GB, right? My process is small. The process P is currently just using 2 GB. Sorry. So let me write here. The process is just using. I mean, it is not just, but yeah, in compared to the virtual address space, I'm just saying just. Okay, just using 2 GB. Now, what they're saying is that the minimum amount of memory required for the page table of P across all the levels is how many KBs? Okay, the minimum amount of memory using the multi-level paging, and the multi-level paging is given to us. This is the first level, second level, like that. Okay, so let's just see. So in terms of pages, can you tell me how many pages I'm using? Number of pages the process is using. Process is using. It is 2 GB, means this is 2 into 2 power 20 upon the page size is 2 power 12, which is 2 power 8 into 2 power 9, right? 2 power 9 pages. So we are just using 2 power 9 pages. Is this okay to everyone? Let me know if there is any doubt. So we are using 2 power 9 pages, and out of how many pages? Maybe I think this is 9 plus 9 plus 9. Out of 2 power 27 pages, we are just using 2 power 9 pages. See, this is your virtual address space, right? They are saying this is your virtual address space. In this, you have 2 power 27 pages total. Okay, in terms of pages, I am saying this is 2 power 27 pages you have total. But you are just using 2 power 9 pages. Let's suppose these are the 2 power 9 pages. Your process is just using 2 power 9 pages. Now tell me, for the first level paging, okay, so maybe I can copy it. For the first level paging, how much space you need? Oh, sorry, how many entries you need for the first level paging? Just tell me. Okay, so for the first level paging, since you are just using, since you are just using 2 power 9 pages, that is why here, okay, either you say first or third, I mean they are saying third. So here you will be needing 2 power 9 entries, right? So you will be needing 2 power 9 entries, which is same as, since each chunk is having 2 power 9 entries itself, because this is 9 bits. So which is same as just one chunk, right? This is same as one chunk, which means just one entry here, right? Which means just one entry here, and one entry means one chunk. I mean, at least you will be needing one chunk, which means if this is one chunk, then it is just one entry here. Actually, you just need one entry here, right? So which means just one chunk. So at every level you just need one chunk. Let me know if that is fine to everyone. Okay, this is 2 power 19. I didn't get you. Okay, let me just check. Uh, have we done some mistake? These are 2 power 9 pages, right? I didn't get it, Samant. What you're saying? 2 power 19 is what? See, this is virtual address space is these many GBs. That is okay. Process is just using 2 GB. 2 GB means, oh, yeah, it is 30. Yeah, sorry, it is 30. So it is 30. It means that is like, I think I need to add 10 here, which is 2 power 19 pages. This is 2 power 19 pages. Sorry. Okay, no problem. This is 2 power 19 pages, and this since because of 2 power 19 pages, I will be needing 2 power 19 entries. Now, can anyone tell me, because of 2 power 19 entries, how many chunk I will be needing? Each chunk is having 2 power 9 entries, so 2 power 19 upon 2 power 9, which is basically 2 power 10 chunks I will be needing, right? These many chunks I will be needing. So let me write it here. These many chunks I will be needing. So here 2 power 10 chunks. Let me know if that is fine to everyone. Right now, if it is 2 power 10 chunks, so that is why at this level you will be needing 2 power 10 entries, which is equal to 2 power 10 entries. And since it is 2 power 10 entries and each chunk is having 2 power 9 entries, so that is why there will be 2 power 10 entries upon 2 power 9, which means you will be needing 2 power 1, which is 2 chunks you will be needing here, right? So you will be needing 2 chunks here, so that is equal to 2 chunks. And now, since because of these 2 chunks you will be needing 2 entries here, and which means you will be needing 1 chunk, right? At outermost you always need 1 chunk. So basically this is these many chunks you will be needing at every level. So let me just tell you that how many chunks we are using at every level. So at this level, I think I will always be needing the whole chunk, which is 1 chunk. At this level I need 2 chunks. At this level I need 2 power 10 chunks, right? I hope that is fine to everyone. Now this 1 chunk means how many entries? I actually need 2 power 9 entries. Okay, this 2 chunks means I need 1 chunk is 2 power 9 entries. This means 2 into 2 power 9 entries. This is 2 power 10 into 2 power 9 entries, right? So let me just sum this up. So you can sum this up. It will be 2 power 9 plus 2 into 2 power 9 plus 2 power 10 into 2 power 9. This is just entries, not in bytes, right? So if you take maybe 2 power 9 common, it will be 1 plus 2 power 10 into 2 power 9 entries. Again, it is just entries, and they have given one entry size, I think. Yeah, this is 8 bytes, right? So you can just multiply by the 8. So which is 1 plus 2 plus 2 power 10 into 2 power 9 entries into 8 means 2 power 3 bytes. So which is coming out to be, this is okay, they want in KB, right? They want the answer in KB. Okay, so kilobytes, they want the answer in KB. So that's why let's just convert that to first KB, which means 2 power 9 into 2. So this is just 4, right? This is just 4 KB. So I will be just writing 1 plus 2 power 10 into 4. I mean, okay, let me just write this way, into 2 power 2 into 2 power 10 bytes. I'm just taking this 2 power 10 and 2 power 2 separate. Now this is what they're asking, right? This will be in the KB. So which means this is 2 power 10 is 1024 plus 3 into 4. So this number is equal to 3 plus 1024 into 4, which is coming out to be 1027 into 4. Now let's just do this calculation. uh, let me just show you 10, okay, 1027, yeah, 14108. This is 410, right? So these many kbs, that's what they're asking in the question. So 4108 is the correct answer. Let me know if that is clear to everyone or there is any doubt. Have you understood this question completely? See, what we are doing at every level, we are just maintaining the minimum entries that are required, right? At every level, we need 2 power 19 entries because I just need to refer 2 power 19 pages. So these are the minimum entries that is required at this level. These are the minimum entries. These are the minimum entries. So based on that, these are the chunks I required. These are the chunks I required. So at every level, I'm just looking for what are the minimum entries I required. No, to solve, to serve any virtual address translation to the physical address translation. Right, I don't need more than 2 power 19 entries because only 2 power 19 pages are useful here. I will never need to refer this page, right? I hope that is fine to everyone. Okay, Devanjan is saying it is clear. Cool. So now let's just move to next question. So this question has been asked very recently, and now what you can do? Okay, let's just do it quickly. Can you quickly tell me what is the size of the flat level page table? So this is the size if you use multi-level page table, right? What is the size if we use only just flat level page table? So see, uh, sorry, in case of flat level page table, let me just copy it. See, you will not be having this address split. So in case of flat level page table, you will just say that there are how many entries here? This is okay. So this is the page offset is 12 bits. That is okay. But at this level, how many entries you will be having? You will be having 9 plus 9 plus 9, 2 power 27 entries you have for the flat level page table, right? 2 power 27 entries you have for the flat level page table. 2 power 27 entries. Actually, it doesn't care that if out of them only 2 power how much? 2 power 19 are useful. Okay, I mean 2 power 19 pages are useful. So 2 power 19 entries actually useful only. 2 power 19 useful, but it doesn't care. I mean, you have to have the whole page table because just a flat level page table. You can't divide it, right? So that's why you have to have this whole. Out of this 2 power 27 entries, only 2 power 19 are useful, but that's okay. I mean, you can't do anything. So 2 power 27 entries you need to maintain. So which means 2 power 27 into 8 bytes, right? Which is 2 power 3, which is 2 power 30. 2 power 30 bytes you need to maintain, which is 1 GB. So using the flat level page table, you need to maintain 1 GB, and using just multi-level page table, these many kilobytes only, right? These many kilobytes only. See how big is 1 GB and how small is this many kilobytes. So that's the benefit of using multi-level paging. So multi-level paging actually reduces the size of the page table because you only get to store what is needed, right? Okay, I hope you understood. Now let's solve this question. Okay, this question has been asked in GATE 2003, but before that, I just want to solve one question which has been asked in one university. So let me solve the second part of this question. So as I said, the first part, I mean, actually, this is just a common question. So like the first part has been asked in one PYQ, another part they have asked in another PYQ. So let me just go to this question again and let me solve the third part of this question, right? Okay. Yeah. So I hope this question is visible to everyone. And now let's just solve only the third part. What they're saying here, here they just want to modify the question little bit. I mean, this is almost same as the second part, but with little modification. What they're saying is that uh, this is the address split as usual, but earlier in the second part, if you remember, they said the process is using. Let me just show you the second part. Okay, they said the what is the page table of the process if the process is using 256 kilobytes. But now in the third portion, in the third question, they are saying the process is using maybe 256 or lesser than 256 or something, but this is in the different area, which means earlier they said that starting from 0 you are using 256, but now they are saying that okay, the process is using 48k and then 600k and then 64k, but at the different locations. Okay, that's the only difference. So let's just see that how to solve this kind of question. Okay, so what they are saying is that what is the size of the page table again, right? Earlier also they have asked the size of page table, now also they are asking the size of page table, and now what they are saying that what is the size of page table if the process is using 48k starting from this address and 600k. So basically the process is using 48k plus 600k plus 64k, right? Plus 64k. But now they are saying it is at different address. What do I mean by that? They are saying that maybe the 48k is here, okay, 48k data it is using here, maybe it is stack, I don't know actually, right? Maybe let's suppose that this is 64k, okay, and maybe let's suppose this is 600k, something like that. They are saying that at different locations we are using, and in between something empty is there, okay? Some empty portion is there. That's what they are saying. So why this question is little tricky, I mean, compared to the earlier question? Because earlier I just needed to calculate that okay, how many pages I'm needing. So let's suppose earlier I said like 2 power 10 pages I need, and then 2 power 10 entries I need here, right? 2 power 10 entries. But here the question is little tricky. Reason being is that let's suppose okay, I'm giving you one extreme case. Let's suppose there is a process that is using one page here and another page here, one page here, just two pages here. Now tell me how many entries you need here, number of entries in the last level page table, in the third level page table, how many entries you need? You need two entries, right? And each chunk is having, let's suppose okay, I mean, let's suppose that this is the same split that we have, okay. So suppose just a hypothetical question, just to make you realize that what is the difference between these two questions. So suppose this is the current scenario that I'm using one page here, I'm using one page here, so I just need two entries. But unfortunately the tricky part is that I need these two entries at different chunks. I mean, I still need two chunks, right? Because the first entry will be in the topmost chunk that I need. So this is the first chunk, right? There are how many chunks? There are many chunks actually. Each chunk is having 2 power 6 entries, and similarly this is the last chunk. It is also having 2 power 6 entries, right? I need one entry here that will point here. I need one entry here that will point here. So actually I still need two chunks. That's the problem. If I'm not using pages continuously, then it becomes little tricky. Yeah, thank you, Arnab. Arnab is saying that amazing intuition from Go classes. Thank you, Arnab. Thank you so much. Okay. So I hope everyone understood this. That what we are trying to say. So if you're using the pages at different locations, then things might get little tricky. So that's what we want to address in this question. Okay. So what they're saying that 48k I'm using starting from this address. So see how many bits I have in the virtual address space. The total number of bits I have in the virtual address space is 32, right? 32 bits. And now since it is in hexadecimal, so they are saying, let me just write it. From starting from this address, I'm using 48k. So how many bits are they? 32 bits is my virtual address space. So this is 1, 2, 3, 4, 5, 6, 7. 7 into 4. These are the 28 bits. So maybe let me just append 0 just to make it 32. So they are saying that starting from this address, okay, 0 was optional because you do not always need 0. So basically this is 0, 1, 0, 0, 0, 0, 0, 0. This is in hexadecimal. So these are the 8 octet I can say, and which is equal to 32 bits. This is just 32 bits, which is my virtual address space. So they are saying your virtual address space might go, okay, this is your virtual address space that might go from 0, from 80, I mean in the hexadecimal it is 80 to FFF, right? So this is your virtual address space, and somewhere in this virtual address space we are using 48k that will start from this particular address, which is, let's suppose somewhere here this address exists, and that is 01000000, right? From here, from this address, let's suppose 48k is this one. This area is 48k which I will be needing. Is this fine to everyone? This area is 48k. Okay, that may be the stack area, maybe the heap area. Let's not worry about this area, but yeah, I will be just using this area, right? Okay. So can you tell me one thing, very interesting thing, is that if if this is one of the address that I have, can you just tell me the next address? I mean, just address above it. Maybe you can say you just need to add one, because see it is a byte addressable, so every byte is having one address. So this is the address of one byte. I mean some byte, and if you add one, you will be getting the address of just next byte, right? So if you add one, you are crossing one byte. And let's suppose these are the 48 kilobytes that I have. So suppose this 48 kilobytes, I'm just approximately I'm writing it is 48 instead of 48. I'm just writing it 64 is the closest number, right? Okay, 64 kilobytes. Okay. See what I want to say, that I want to just calculate this number. I hope you are fine with this. Basically, I just want to add 48 kilobytes to this. Okay. So this address is given to me, and I want to just calculate some another address that is after the 48 kilobytes. Okay, I want to just calculate this particular number. Is this fine to everyone? Just for my sake of curiosity, I mean that has not been asked in question, but just to understand this question little bit better. Okay, let me know if you have understood my plan. So my plan is that I want to calculate some number which is after 48 kilobytes. Maybe let me just say approximately it is 64 kilobytes, although it is not, but approximately, which is actually same as 2 power 6 into 2 power 10, which is 2 power 16 bytes. So if I add, if I just want to cross one byte, I need to add one. If I want to cross 2 power 16 bytes, I need to add 2 power 16. Very simple, right? 2 power 16 means that it will be 1 followed by 16 zeros, right? So maybe I need to add followed by 16 zeros. 1 followed by 16 zeros means that since every zero is the 4 here, so basically I think I need to add 1 followed by 16 zeros. These 4 are basically 16, which means that if I add this particular 48 kilobyte, then probably I will be having some address which is looking like approximately. I will be having this address which will be looking like after the 48 kilobyte. Okay, I mean that address is in fact after the 64 kilobytes. After the 64 kilobytes, I will be having some address which is something like this: 010100, right? Is this okay to everyone? Even the 48 kilobyte actually will end before it, right? 48 kilobyte will end before it, and after the 64 kilobytes, I will be having some address. And I mean, they have not asked that what address you are having, but currently I am just telling you this. Okay, cool. Now, okay, what they are saying is that I don't know if I'm making this question complicated or not. I mean, I just wanted to give you the bigger picture of this question. Okay, that's why I'm just calculating some numbers which might not have been asked directly in this question. But anyway, if you are starting from here, you will end somewhere near to this, right? You will end somewhere near to this, and this portion is actually allocated. And now you're using 600k that is starting from this address, right? So they are saying you're using 600k that is starting from this address. Now, let me go to the next page. So let me remove this. Okay. So they are saying that you are starting from this address, and this address is, can you just check if it is 32 bits or not, or should I prepend some zero? I think this is the 32 bit, right? Okay, great. So they are starting from this address, and then they are saying that you are using 600k starting from this address. Can you tell me where is this address, just to check it? Okay, maybe this address is I think this is all zeros. This is starting from 8. Oh, too far. I think this will be somewhere here, right? Maybe too far from these addresses. Anyway, let's not worry about where this address will be, but just to you know take little bigger picture, I'm just saying it. This address is somewhere here. little too far from what I already have. That's not a problem. Cool. Now, from here, they're saying that you are using 600K, right? So maybe let's suppose this is the 600K, 100 kilobyte. Can you just add a 600 kilobyte number to it? And then can you just tell me what you will be getting? I think this is 2 power 10. This is 600. Let me just approximate is 1024 kilobyte, okay? Which is 2 power 10 into 2 power 10 bytes, which is 2 power 20 bytes, right? If you add 2 power 20, which means 1 followed by 20 zeros. 20 zeros means here one is okay. These are the 20 zeros, 16 and 20. I think you need to add one somewhere here, right? I'm just approximating actually. You just need to add one somewhere here. So which means 0x80100000. Is this fine to everyone? So maybe I'm just approximating that what should be the address after the 600K. So anyway, like there will be some address after the 600K which will look something like this: 0x80100000. Is this fine to everyone? Okay. Now what they're saying that okay, after you are using this, and then you are using 64 kilobytes starting at this this address, right? Which is 0x. Okay, you are using 64. Just last thing that you are using is 64 kilobytes, which is starting at this address. So from this address, you are using 64 kilobytes. Can you just check if it is 8 or not? I mean, this is 32 bit or not? I think this is 32 bit, right? See, this is 32 bit. So from here, you are using 64 kilobytes. So maybe this is somewhere okay. Maybe this is far from this address also. So this is somewhere. Let's suppose here. So let me just make the diagram little more clear. So let's suppose your address which you are talking about is somewhere here, right? So this address is somewhere here, and from this address there is 64K that you are using. Okay, let's not worry about that. What will be the number after that 64K? I mean, you can easily calculate. This is 1 followed by I think 16 zeros, which means I mean you need to add 1 here, right? So maybe you can say that the number after the 64K will be something like this. Number after the 64K will be maybe something like this. Anyway, these numbers are not much important. I mean, not I think not at all important. But anyway, let me just write it. So this is 64K, right? So this area is allocated. This 600 KB area is allocated. This area is allocated. So they are allocating these three areas. Let me know if that is fine to everyone. I mean, this calculation was not at all important, but I just want to see that okay, what is happening here. Is this fine? Now, what they're saying that if you're using this kind of, I mean, if your process is using this kind of things, then what should be the size of the page table? Can you quickly convert this 48 KB in the number of pages? So the page size is 2 power 8, right? So just convert that to number of pages. So how many pages we are needing at every section? So see. So let me just do one thing. Maybe I can. Okay. Now tell me. See, this is 2 power 8 is page size, 2 power 8 bytes. This is 48 kilobytes. So 48 kilobytes upon 2 power 8, 2 power 8 bytes, right? So these are the pages that we are using. So which is basically 48 into 2 power 10 upon 2 power 8, which is 2 power 2 will be here. So 48 into 4, right? So it will be 2 power 2 and then 48 into 4. Let me just do it. 48 into 4 will be 192. So I think we are using 192 pages at this moment, right? Is this okay to everyone? Pages here. So this is 192 pages. This is 190. Let me know if this is understood or there is any doubt till this point. I mean, this complete diagram and how we are calculating the pages and everything should be clear. Let me know if there is any doubt. If you do not have any doubt, then we will move further. Otherwise, we will just talk about this thing only. Is this okay to everyone? Okay. Let me know if there is any doubt. Still, if you have any doubt, you can just tell me. Now, can you convert for everything? Can you convert that how many pages I need at every moment? So this was 192 pages, and then similarly, or maybe just I can write the 48 into 2 power 2 pages. Okay, if this 192 is coming from 48 into 2 power 2. This is 48 into 2 power 2 pages I need here. Similarly, if you do this, this is actually 600 into 2 power 2 pages. Similarly, if you do, then it will be 64 into 2 power 2 pages. So these many pages I need at every section. So now can you tell me number of entries that we need? Number of entries. See, because of this, I need how many entries? Can you tell me the number of entries that I will be needing at this? See, each page is just one entry, right? So each page is one entry, remember it. So basically we need, let me just write it, 48. Because of this chunk, we will be needing 48 into 4 entries. Because of another chunk, which is this chunk, right, I will be needing how many entries? 600 into 4 entries. Because these many pages we are using, and each page is just one entry. And for this, I will be needing 64 to 4. Is this okay to everyone? Now, can you tell me how many chunks we will be needing? See, just check that here each chunk is having 2 power 6 entries, right? Each chunk is having 2 power 6 entries. So if these many entries I need, then you divide with the 2 power 6. So 48 into 4 upon 2 power 6. These many chunks you will be needing, right? Which is coming out to be, can anyone calculate it quickly? It will come out to be 3 chunks. So you will be needing 3 chunks here. Similarly, you need 600 into 4 entries, which means upon 2 power 6 chunks. If you just calculate it, I think it will come out to be 38 chunks, right? So this is 38 chunks you need. And then here you will be needing 64 into 4 upon 2 power 6 chunks, which is 4 chunks. Right? Let me know if this calculation is clear to everyone, like what we are doing, what we are not doing. So now you know that at this level, how many chunks we will be needing total, right? 4 chunks, 38 chunks, and 3 chunks. Now can you just see what is the answer? So basically, let me just calculate. Now it is very easy, right? Now it is very easy. I mean, earlier also it was very easy. I just calculated the end address. All that was not much needed. So now so because of this 4 chunk, I will be needing, I will be needing 4 entries here, right? 4 entries means this is one chunk is having 2 power 8 entries. So because of this, I need one chunk. Because of this, I need one chunk. Because of this entries, because of this I need one chunk. Because of this I need one chunk. So total 3 chunks I need, and because of this, I always need one chunk at the last. So let me just tell you that how many chunks you are using totally, right? So basically you need one chunk at the last, obviously. So at this level you need one chunk. At this level you need 3 chunks, right? Because of this 3 1 1 1. And at this level you need 4 plus 38 plus 3. 4 plus 38 plus 3. Now let's just convert this chunk into the entries. One chunk means 2 power 10 entries here, plus 3 into 2 power 8 entries here, plus 4 plus 38 plus 3 into 2 power 6 entries here, right? So these are the entries that you have. Now let's suppose if page table entry size is, let's suppose 2 bytes, then you can easily convert that to bytes also, right? Which is equal to into 2 bytes. So this is the answer. Let me just see if the answer is matching. See here. Okay. See, I have multiplied 2 at the end, but they are multiplying in the between. 38 plus 4 plus 3, right? They are multiplying in between, that is okay. Into 64. 38 plus 4 plus 3 into 64. 38 plus 4 plus 3 into 64. Yeah, this term is matching. Yes. Okay, this term is matching. Another term is 256 into 3. Into 2 I am doing at the end, right? Into 2, let me just cross out this 2. So basically into 2 I am doing at the end. So 256 into 3 should be matching. 256 into 3. So 256 into 3 is matching. And then 2 power 10 into 1, right, is matching, right? So 2 power 10 into 1 is also matching. So yes, this is the correct answer, right? 2 I am multiplying at the end. Let me know if that is understood to everyone. So basically, this is just an easy question. I mean, I do not need to make it complicated. You just need to check. Okay, this much KB, this much KB, this much KB. It means how many pages. So since you are using it at different places, that is why these chunks will be the different. I mean, this is just 4 chunks that you will needing at this level, and because of this 4 chunks, there will be 4 entries that will be in just one chunk. Okay, so you need 3 chunks here. Just one chunk is not enough. Although the total number of entries you need to maintain at this level is 4 plus 38 plus 3. One chunk can hold all of the entries, but there are different at the different places. So that's why you need 3 chunks, right? Why that 3 chunks came? Okay, this one you are asking. Let's suppose this is the first level, this is the second level, this is the third level. So this is the first level. Okay, sorry, the third level. This is the second level, and the one chunk I need at finally, which is at the first level. So which level you are asking? Yeah, at the different locations. Yes, right. Okay, so I will clarify it more, that how to be 100% sure that that I will be needing 3 chunks or not. So let me just go to one of the gate PYQ, and there I will be just clarifying this concept more. Okay, so let's just start with this question. This question has been asked in GATE 2003, and this question is on the similar lines, right? So let's just solve this question. So what this question is saying, a processor uses 2-level page table for virtual to physical translation. Page tables for both levels are stored in the main memory. Virtual and physical addresses are both 32-bit wide. So they are saying we are using 2-level page table to virtual and physical. Page table and for both levels are stored in the main memory. Virtual and physical, both the addresses are 32-bit. Okay, virtual address space and the physical address space, both are 32 bits. And then the memory is byte addressable. For virtual to physical address translation, the 10 most significant bits of the virtual address are used. Okay, so they are saying that for virtual to physical translation, the 10 most significant bits of the virtual address are used at the index to the first level. Most significant 10 10. So they are saying 10 10 12. They are saying that the address division for the virtual address space is something like this. Okay, this is the virtual address space, and the address division is 10 10 and 12. That's what they are saying. 12 least significant bit are used as an offset within the page. Okay, assume that page table entries, both level page tables are 4 bytes further. So they are saying the page table entries is of 4 bytes. Further, okay, this particular TLV information is not required to what I want to solve. So that's why I'm just removing this TLV information. Okay. Okay. Now they are saying that this information is given to us. Now they are saying suppose a process has only the following pages in its virtual address space, two contiguous code pages starting at this virtual address. So they are saying two contiguous code pages that is starting from all zeros, right? So maybe it is using the number of pages. So it is actually telling you the pages that we are using. So two pages starting from this all zeros, right? Two pages here, they are directly giving you the pages. Two pages here they are saying, right? Two contiguous data pages and two pages that is starting at this address. Two pages here. So this is using maybe two pages from here. Maybe this address will be somewhere here, I don't know. So let's suppose that two pages from here, right? And then they're saying, and one page at this address, one page at this address. Maybe somewhere here, I don't know where this address, but yeah, let's suppose somewhere here. So one page I'm using at this address. And this is your virtual address division, right? I hope you understood the question. So now what they're asking, that what is the minimum size of page table that you need, right? Okay, can you just give a wild guess? What do you think could happen in the best case? Best case means, maybe see how many entries you need here. You need one entry because of this one page, right? You need one entry here. You will definitely need two entries here. You will definitely need two entries for this. Now in the very best, in the best to best case, what may happen, all of these entries you might store in just one chunk. See, there is a chunk size. Each chunk can hold 2 power 10 entries, right? Each chunk can hold 2 power 10 entries. So it might so happen that all of these entries could be in just one chunk, right? See, you will anyway will be needing one chunk at this. So here you will be needing one chunk, that is for sure, because it is the outermost. The only question is that how many chunks you need here. In the worst case, maybe this one entry could go to one chunk, right? These two entries could go to different chunk, and these two entries could go to different chunk. So in the worst case, what do you think? How many chunks I will be needing at this case, at this level? How many chunks you will be needing at this level in the worst case? I think there will be three chunks, right? One entry this one entry, which is the topmost entry, can go to the one chunk, and next two entries, which is for this, can go to some chunk which is not in this chunk, right? I mean, these two entry go to some other chunk. It depends that how many gap. What is the gap here, right? What is the gap here? It depends on the gap. So these are the gaps, and this is filled. So it depends on the, if gap is very large, if gap is very large, then you will be having these entries in the different page table, right? If the gap is very large. So let's suppose the gap is actually very large, and this is, I mean, I'm just guessing it. I'm not saying that this is true, but I'm just guessing it. Okay. So let's suppose I have not calculated it manually. Okay, mathematically I have not calculated, but let's suppose maybe the gap is very large. I mean, okay, I'm just assuming that gap is very large. In case if gap is very large, then in this case, can you tell me how many chunks you will be needing? You will be needing three chunks here, right? You will be needing three chunks. So basically, you need one chunk at the outermost. You need three chunks here. And so how many total you need? Total you need maybe, like, I mean, total you cannot directly add, but yeah, anyway. So you need basically four chunks, right? So I mean, this is just my guess. In worst case, you might be needing three chunks here. This is just my guess, right? Okay. So which means maybe I can say that here you need three chunks. Okay, I have not actually calculated the gap and all, so we need to, I think, do it. But yeah, this is three chunks, which is actually mean 3 into 2 power 10 entries. This is one chunk, which is actually mean 1 into 2 power 10 entry. So basically 4 into 2 power 10 entries you need. Okay, it is just actually my guess. In first case, I actually need to maintain these many entries, which is actually equal to page table entries 4 bytes. So that's why it is 4 into 2 power 10 entries into 4 bytes, which is actually 16 kilobytes. Right? In worst case, right? If the gap is very large, if your data is not very contiguous, then you will be needing 16 kbs. Let me see the answer. Okay, one chunk you need here, 3 chunks you need here, 16. Okay, whatever I guessed actually seemed to be correct answer. You actually need 16 KB. But let's be 100% sure that we need 16 KB, which means, I mean, actually in the exam also, if you do with this way, then most probably your answer will be correct, because generally these gaps are too large. But let's be 100% sure if this gap is too large or not. Okay, so let's just check if this gap is too large. I hope you understood that what I'm trying to say, right? See here. So how many entries you have total? Can you tell me? See, this is 10, 10, 12, right? The address split is 10, 10, 12. So how many entries you need in one chunk? How many entries you have here? 2 power 10 entries you have, right? So here you have 2 power 10 entries, which means if this gap, if this is 2 power 10 entries, if this gap is almost 2 power 10 pages, right? If this gap is almost 2 power 10 pages, if this gap is 2 power 10 pages, then this next thing will definitely go to the separate chunk, right? Is this 2 power 10 pages or not? That's what we need to check. See, this is too far. I think this is F. I think this is F. This is just 0. I think this is too far. One page is 2 power 12. So basically, you can even calculate it exactly. 2 power 10 pages means these many bytes, which is 2 power 22 bytes, right? 2 power 22 bytes, which means 2 power 22 means this is okay. This is 4. I think 5 zeros. You just need to skip 5 zeros or 5 or 6 zeros. These are the 8 zeros. So I think definitely this gap is too large, right? I mean, after 5 zeros, it will be 2 power 20 and 22. Maybe you need to add 1 here just to bypass this 2 power 22. But yeah, this is F. So to reach here, this is too long, right? So I think this gap is sufficient enough. I'm just guessing it. Most probably it should be sufficient enough. I mean, numerically also I'm trying to establish this connection. Similarly, here also this is starting from 0 and this is 004, right? So I think I mean, if you even if you add 1, you will be adding one somewhere here, right? I mean, you just need 2 power 22 bytes. So 2 power 22 bytes means you might be adding 1 here, and it is actually 4 at this bit, right? 4 is here. So maybe this gap is also too large. So since these gaps are too large, so that's why these entries will go to different chunks, right? So this will go to different chunk, this is to the different chunk, this is to the different chunk. I hope you understood this, right? So that's also like little I mean little better if you just quickly check if these are going to the different chunks. I mean, you just need to check this gap, and how we are checking this gap is basically this chunk will be having 2 power 10 entries. So you should be having 2 power 10 pages. If that is after 2 power 10 pages, then this gap is sufficient enough. I mean, large enough, very large gap, right? I'm just calling it a large gap. Okay. So I hope now you understood. So basically, this is the answer. And just to make this answer little bit, I mean, just to improvise on this answer, you can actually calculate the size of the gap, and you can say that, okay, because the gap is too large, that is why you are going to the different entries. And anyway, like you will be getting the same answer. Now, can you do it using the flat level page table? I think we can quickly do it. So using the flat level page table, if I do, can you tell me the size? So it's very easy. Using the flat level page table, it is basically 2 power 20 entries, right? 2 power 20 entries. Each page table entry, as they are saying in this question, is 4 bytes. So 2 power 20 entries, which means 2 power 20 into 4 bytes, which is actually 4 MB. See, using the flat level page table, you need 4 MB of page table, and here you just need 16 KB. So how much drastically you are reducing? And how you are reducing? You are actually not saving. You are not saving the pages. You are not saving the entries for this. I mean, there might be some chunks which are totally invalid, right? There might be some chunks which are totally having all the invalid entry. You are not saving this chunk anywhere. So that's how you are saving the space. Is this fine to everyone? So that is the concept of multi-level paging, and now like we have understood everything about the multi-level paging. If you put yesterday's video and today's videos together, then I will say that this multi-level paging is completely covered now, right? Okay. Let me know if there is any doubt. Now I want to move to some different questions, but I think we do not have the sufficient time. So I will take a class in the morning. Okay, and there are few questions that I want to solve. So I will take a class in the morning, and that will be a short class where I will be just solving few of the questions which are related to TLB, related to page fault and all. Okay. So let's end this today's class. If you have understood everything, please just comment it out. Please let me know if you have actually understood how the multi-level paging is working. Right? If you have understood these questions, which are very, very tricky questions, then please just comment it out. Thank you everyone. Thank you. Take care. Bye.